Hi, I'm Eric from Grant Group, University of Wisconsin-Madison. And today I'm going to share with you a story about coil-stretch-like transition of soft elastic sheets in extensional flow. This work is supported by National Science Foundation. The freely suspended deformable sheets are commonly observed in many synthesis or processing stages and are widely applied in many fields, such as polymer sheets as basis of a self-propelled biohybrid device or hydrogels as a substrate of an origami-inspired structure. Here are pictures of two-dimensional kinetoplastic DNA sheets found in biological systems. However, so far there has been very little literature related to the dynamics of a sheet-like particle in fluid, which motivates this current study. In many of the scenarios that we care about, the sheet has very small size, and it is reasonable to assume that the particle Reynolds number, defined here, is much smaller than unity. So the scenario becomes Stokes flow. Polymer, a very classic soft particle, is known for an interesting phenomenon called coil stretch transition. A linear launching polymer may exhibit abrupt transition in conformation from a coil state to a stretch state within a very small change of flow strength. Based on this, an interesting theory first proposed by Dijen in 1974 that the polymer may have multiple steady-state conformation as hysteresis under the same flow strengths based on its deformation history, or bistability. The hysteresis has been numerically observed by Fu and Liu by a nonlinear dumbbell model with conformational dependent drag, as shown in this plot as polymer end-to-end distance versus flow strength. The curve changes from monostable to bistable with increasing friction coefficient. This phenomenon is also being experimentally confirmed by Schroeder and co-workers around 2003 with a dilute DNA solution. Here, the plot with polymer extension versus dimensionless flow strengths clearly shows a bistable regime, where the final conformation of the polymer inside this regime depends on whether it starts from initially coil state or initially stretch state. Outside this regime, the polymer becomes monostable. The cause of such bistability is found to be related to the intramolecular hydrodynamic interaction and the polymer material properties such as chain length. The above observation let us think whether there exists a coil-stretch-like transition for soft elastic sheets in planar extension or other extension flow fields. To investigate this kind of problem, we built up a model by simulating an incompressible sheet. The sheet is neutrally buoyant in unbounded flow field. The sheet itself satisfies no slip and no penetration condition on surface and the traction-free edge. In this study, we consider three rest shapes and three different extensional flow fields shown here. A here is the characteristic length scale, and epsilon dot is the flow strength or elongation rate. As for the sheet itself, we care about two types of elastic mechanical responses, the in-plane deformation and the out-of-plane bending. We numerically solve the deformation by a finite element-based method for discretization to the surface with nodes to form triangular elements. The nodal forces are evaluated by first variation of corresponding strain energy. The shear strain energy is evaluated by integrating a local areal strain energy density W across the sheet surface. Here, we choose Young model, a model used to model a rubber-like cross-linked polymer structure. Lambdas are the local principal stretch ratio, and G is the 2D shear modulus. C here, as the weight of this qubit energy term, is a very important parameter. It determines whether the material is string softening or string hardening, and is physically related to numbers or inversely proportional to numbers of polymer segments in the structure we're simulating. When C equals 0, the model decays back to a very simple Neo-Hookean model. As for the bending, we just simply sum the penalty energy due to the deflection between neighboring elements. Therefore, we can define two dimensionless groups. Kappa number, essentially the dimensionless flow strength, compares the flow to in-plane deformation. Larger Kappa number indicates the sheet is more deformable. KB hat as dimensionless bending stiffness. Smaller KB indicates the sheet is easier to deflect. Here, one thing to note here is that Kappa number over KB hat is the actual parameter that compares the flow strength to bending. Previously, we mentioned that we assume it is in Stokes flow. Thus, the total nodal elastic force is balanced with the hydrodynamic force from the flow field. The Graphing equation is the Stokes equation and continuity equation. We solve for velocity with the method of regularized Stokes-like indicated here. And we present you a validation case to our model with a rigid disk in biaxial flow, as indicated in the figure on the right, where we compare the perturbation velocity norm around the disk with an analytical solution we derived. The results here showing in the figure shows perfect agreement. Okay, now let's start introducing the dynamics in planar extension first. The first thing I want to introduce is a stable steady state for all the shapes. There are two important conclusions. First, for any shape of a deformable sheet, a stable steady state is always aligned with the xy plane. I use a disk here as an example. This indicates, like as you can see, it finally wrinkles, but finally goes to the xy plane. So this indicates that a flat sheet is always the final conformation, and therefore only the in-plane deformation or Kepler number matters. Bending only play a role during the transient process, and we will not discuss the dependence of bending stiffness in the later results in planar extension. Second, we notice that for some non-circular shape like a square, it has a preferred stable orientation as the diagonal aligned with the flow direction shown in the video here. Okay, we now consider a simple Neil-Hookean case. Here, the plot indicates the stretched lengths with increasing Kepler number of flow strands for different shapes. The way of measuring the stretched length is indicated on the right here. We found that for every shape, it will stretch without bound after reaching a critical Kepler number, shown here. This is very similar to the case of a simple dumbbell model without hydrodynamic interaction. Because the Neil-Hookean model is strain softening and we're not able to capture a fully stretched state, so we switch from the Neil-Hookean to the Young model. Here, as you can see, a disk with Young model, just in a very small change of Kepler number, the sheet goes from what we call a compact state to a fully stretched state. We call this transition, similar to the coil-stretch transition, a compact stretch transition. Another interesting fact is that, similar to hysteresis behavior found in polymer, we found that the sheet has multiple steady state within the same Kepler number, depending on its deformation history. As you can see, an initially compact sheet arrives at a different steady state compared to an initially stretched sheet. This happens because when the sheet is initially stretched, there is a big difference in the surface area contacting with the flow compared to the initially compact case. The strong hydrodynamic interaction between the flow and the sheet surface help to maintain the current deformed state. And we will address the role of hydrodynamic interaction in the later slides. Okay, now let's summarize a disk case. On the left, the figure kind of concludes previous two interesting phenomena we observed. So let's spend some time understand this diagram. Similar to the polymer, a deformable sheet has or deformable disk here has a compact branch and a stretch branch. We define two critical Kepler number here, CAC, for the largest Kepler number that it can stay at a compact state. Beyond this Kepler number, if even an initially compact sheet will evolve to a stretch state. And correspondingly, CAS as the smallest Kepler number that can maintain at a stretched branch. Below this point, even a stretched sheet will evolve to a compact state. Those two critical Kepler numbers together marks a bistable regime in between where multiple steady state can be found, with an unstable branch connecting these two branches, but we did not compute this unstable branch. This is an example of two saddle nodes bifurcations here. Inside this regime, the sheet can be either compact or stretched, depending on its deformation history, whether it starts from in a compact or stretched state. However, if we increase C, as a reminder, C here is inversely proportional to numbers of polymer segments we're simulating. We notice that we obtain a continuous curve and the bifurcations vanish, or CAS and CAC merge together to form a continuous curve. So based on the previous two examples, it is clear that a bistable behavior only appears in a certain parameter regime of C. Here, we plot a series of choices of C with increasing C showing the trend. And on the right figure here, summarize the data from the left figure that these two branches were each representing the limit of the compact branch and the stretch branch. We notice that the hysteresis only lives in this gray area marked here, and beyond this cusp point, hysteresis no longer exists. Besides, we also have similar results for bistability for a square and the rectangle shape, which we're not elaborating here. Now we briefly talk about the biaxial extension. Compared with the planar extension, two flow fields share lots of common features, and we just show an example of the transition and the hysteresis parameter regime for each shape indicated here. All right. Previously, we mentioned that one important cause for the hysteresis behavior in polymer is the intramolecular hydrodynamic interaction. Here, so we inferred that the hysteresis in a soft elastic sheet is also due to the AIChE between different parts of the sheet surface. To verify this, we came up with an artificial model that can weaken the AIChE between different parts of sheet structure. This is done by replacing the regularized Stokes-lead with Brinkmann-lead, shown here, a model for fluid passing a porous medium. Such model can screen hydrodynamic interaction because those obstacles in the porous medium help to absorb momentum that achieves a much faster velocity decay rate at r to the negative third power. In Brinkmann-lead, we have a new length scale alpha inverse called Brinkmann screening length. It's relatively a range where AIChE matters. So if alpha inverse r is larger than 1, it indicates that AIChE becomes not very important anymore between different parts of sheet. So here we use a square in both planar and biaxial extension as an example. You can notice that with increasing of alpha, it is clear that in both flow fields, the bifurcations merge and becomes continuous. Thus, we conclude that the hysteresis behavior arises from the AIChE between different parts of the sheet surface. Okay, finally, I want to introduce our ongoing work about compact stretch-like transition in uniaxial extension. Here, the bending start playing a role and the sheet can wrinkle and develop into lots of interesting structure. The figure here shows two choices of bending stiffness. The square marker here shows a disk, shows a flat state where we intentionally enforce the disk to be flat, or we can see it as the stiff sheet with infinite large bending stiffness. So you can see a very familiar bifurcation we saw before. Diamond markers here are a flexible sheet that can wrinkle. As we make the sheet flexible, we notice that there still exists transition and the bistable regime. The introduce of wrinkling result as non-flat conformation that has different stretch lengths compared to a flat state, as you can see here. So here we list some of the very interesting stable steady state conformation we found for both the compact state branch and stretched branch. Interestingly, we also noticed that some data point compared to the CAS for a stiff sheet, the data points here for the flexible sheet might snaps from the stretch branch to the compact branch as indicated for the red here. So far we're still trying to investigate how bending will influence hysteresis, and there are still many questions remain to be considered. As a conclusion, today we show the dynamics of soft elastic sheets in different types of extensional flow and characterize the parameter regime for the hysteresis. Typically, this study might be interesting to those experimentalists who doing experiments related to highly deformable sheets like thin hydrogels. Those kind of structures tend to show bistability with relatively modest extension rate. However, materials with very large implant modulus, such as graphene, might not be the case here since it is very hard to achieve the kappa number in the bistable range. So thanks for coming, and I will finish my talk with a video of the rectangular shape in planar extensional flow. And if you have any interesting ideas, feel free to contact us. Thank you.